Can a moon vanish? Believe it or not, one did, or at least, it seemed to. For centuries, one of Saturn's most peculiar moons, Iapetus, puzzled astronomers by performing what appeared to be the greatest disappearing act in our solar system. First seen in the 17th century, Iapetus would appear bright and visible one day, only to fade into obscurity the next. But far from being a mere optical illusion, this phenomenon was our first glimpse into a world of sharp contrasts, ancient mysteries, and planetary processes unlike anything else we've encountered. Iapetus is Saturn's third largest moon, yet it remains one of its least understood. With a diameter of about 1,470 kilometers, it's not especially massive or flashy compared to Saturn's largest moon, Titan. But what it lacks in scale, it more than makes up for in bizarre, contradictory characteristics. It's a moon split in two, literally. One hemisphere is so dark it absorbs nearly all the sunlight it receives, while the other is coated in reflective ice, making it one of the brightest surfaces in the Saturnian system. The dichotomy is so extreme that it once made the moon vanish from early telescopic views, and it continues to raise questions that scientists are still working to answer today. This two-toned enigma was first observed by Italian astronomer Giovanni Domenico Cassini in 1671. Using the relatively primitive refracting telescopes of the Paris Observatory, he noted that a newly discovered moon orbiting Saturn was only visible when it was on one side of the planet. When it moved to the other side of its orbit, it would seemingly disappear. This wasn't due to cloud cover or atmospheric interference. There was something physically changing in the moon's visibility. Cassini theorized, quite accurately, that Iapetus was tidally locked to Saturn, always presenting the same face to the planet, just as our moon does with Earth. He concluded that one hemisphere of the moon must be significantly darker than the other, explaining why it could be seen on one side of its orbit and not the other. When the bright side faced Earth, the moon was clearly visible. When the dark side faced us, it faded nearly into invisibility. Fast forward more than 300 years, and the mystery of Iapetus has only deepened. While flybys from the Voyager spacecraft in the late 1970s and early 1980s confirmed Cassini's theory of hemispherical brightness variation, they didn't have the resolution to uncover the full picture. That breakthrough would come in 2007, when the Cassini spacecraft, fittingly named after the moon's discoverer, performed a close flyby, passing within just 1,640 kilometers of the surface. What it revealed turned Iapetus from a dot of light into one of the most fascinating moons in the entire solar system. Cassini's detailed imaging showed Iapetus to be a world of radical contrasts, not just in color, but in geology and structure. The dark region, known as Cassini Regio, covers about 40% of the moon's surface and has an albedo as low as 0.03, darker than asphalt. The trailing hemisphere, known as Roncevaux Terra in the north and Saragossa Terra in the south, reflects more than 60% of the sunlight that hits it, gleaming like freshly fallen snow. The result is the highest hemispheric contrast in albedo of any known object in the solar system. And in some places, the dividing line between these regions is shockingly sharp, as if someone had painted the moon in two distinct shades. But how did this dramatic duality come to be? Initial theories speculated that volcanic eruptions from Iapetus' interior might have spread dark material across one hemisphere. However, Cassini's instruments quickly disproved that idea. The dark coating is only about 10 to 100 centimeters thick, and impact craters in the region often reveal bright ice beneath the surface. This suggests the dark material didn't rise from within, it fell from above. Enter Phoebe, another of Saturn's moons, and a key player in solving Iapetus' mystery. Phoebe is an irregular, retrograde moon, meaning it orbits Saturn in the opposite direction from most other moons. Over billions of years, collisions and impacts on Phoebe have ejected dark dust into space, creating a vast, diffuse ring around Saturn. Due to the Poynting-Robertson effect, this dust spirals slowly inward toward the planet. Iapetus orbits Saturn in a prograde direction and much farther out than most other major moons, about 3.5 million kilometers away. As it moves forward through space, its leading hemisphere essentially plows into this inward spiraling stream of dark dust, like a car windshield collecting insects on a highway. The trailing hemisphere is mostly shielded, explaining the stark difference in appearance. But dust deposition alone doesn't fully explain Iapetus' yin-yang appearance. That's where thermal segregation and sublimation come in. The dark material absorbs more sunlight, causing localized warming. Even a slight increase in surface temperature is enough to sublimate water ice, transforming it directly from solid to vapor. Because Iapetus has no substantial atmosphere, the water vapor escapes and migrates. It doesn't drift randomly, it preferentially condenses on colder, brighter areas like the poles and trailing hemisphere. Over millions of years, this process creates a positive feedback loop. Dark areas get darker as ice sublimates away, and bright areas get brighter as they accumulate fresh frost. The contrast becomes sharper, and the pattern becomes more defined. The end result is a world literally split between darkness and light, an extraordinary natural experiment in planetary evolution, still ongoing to this day. And yet, this spectacular albedo dichotomy isn't the only strange thing about Iapetus. The moon's most visually arresting feature is a giant equatorial ridge, a chain of mountains stretching 1,600 kilometers across its midsection. First hinted at by Voyager 2 and confirmed in detail by Cassini, this ridge gives Iapetus a distinctly walnut-like shape. It's a geological structure with few, if any, analogues anywhere else in the solar system. The ridge stands up to 20 kilometers tall in some places, more than twice the height of Mount Everest. It follows Iapetus' equator almost perfectly, and its origin remains one of the most baffling puzzles in planetary science. Several competing theories have been proposed. One of the most widely accepted ideas is that Iapetus once rotated much faster, completing a spin every 16 hours instead of its current rate of 79 days. At that speed, centrifugal force would have caused the moon's equator to bulge outward while it was still warm and pliable. Over time, Iapetus cooled and solidified, preserving the bulge even as its rotation slowed. The ridge, in this theory, is a leftover from that primordial spinning past. Another theory suggests that Iapetus might once have had its own ring system. Material from this ring could have slowly collapsed onto the equator, forming the ridge as it fell. This would neatly explain the ridge's placement along the moon's midsection, but raises new questions about how such a ring would have formed and remained stable long enough to deposit so much mass. Other hypotheses, like tectonic activity, internal convection, or giant impacts, fail to explain the ridge's perfect equatorial alignment or immense scale. No single theory answers every question, and the ridge remains one of the most enduring enigmas in the study of icy moons. The story of Iapetus is, in many ways, a story of firsts. It was the first moon beyond Earth's orbit whose surface features were detected from Earth. It was one of the first clues that celestial bodies could display hemispheric differences. And thanks to Cassini, it became the first place where scientists observed the combined effects of exogenic dust deposition and endogenic sublimation in real time. And yet, for all we've learned, Iapetus remains a mystery. We still don't fully understand the composition of the dark material, beyond it being carbonaceous. We don't know exactly how the equatorial ridge formed. And perhaps most intriguingly, we don't know whether other, yet undiscovered moons or planets might share some of these bizarre traits. Iapetus has shown us that our solar system is still full of surprises, and that even a small, unassuming moon can hold secrets big enough to challenge everything we thought we knew. At the end of the day, Iapetus reminds us of something profound. Sometimes, the most extraordinary revelations in science don't come from the largest planets, the most brilliant stars, or the deepest craters. They come from a dim, distant object that vanishes when we're not looking. From a world that hides in shadow, only to reappear, brighter than before. A place where darkness and light meet in perfect contrast, sculpted by time, dust, and sunlight into a cosmic yin and yang. And so, we keep watching. We keep wondering. Because in the silent, icy stillness of space, even the most improbable places may hold the answers to questions we haven't yet learned to ask.